now I am going to start discussing the principle of another approach which is known as distance based Pareto-GA, in short DPGA. Now, this DPGA is actually found to be efficient to find out that the Pareto optimal front top solution, and we can also solve this particular multi objective optimization problem efficiently. Now, let us try to see the principle of this particular the DPGA. Now, this DPGA, it was proposed by Ositska and Kundu in the year 1995, and here we use a fitness measure to keep track of the progress towards the Pareto optimal front. Now, here what we do is, if you see step 1, the initial random population of the GA, that is capital N, is divided into two subpopulations N1 and N2. Now, N1 is a subpopulation where we use all the GA operators, and N2 is nothing but a subpopulation which contains all the non-dominated solution. Now, to explain it, let me just draw this particular the population. Supposing that this is the initial population N, capital N might be N equals to 1000, and this is generated at random. The solution is generated at random. So, what we do is, so this is divided into two parts, one is N1, one is subpopulation N1 and another is subpopulation N2. Now, this N1 actually all the GA operators like reproduction, crossover and mutation, they are going to work on this particular subpopulation, and N2 contains all the non-dominated solution. Non-dominated solutions are contained in the your N2. Now, N1, as I told, the GA operators are going to work. That means, through this GA operation, it will try to find out some diversification in the population, and there is a possibility with the iteration, the size of this particular N1 is going to decrease and the size of this particular N2 is going to increase. How to do that, I am going to discuss now, but this is the thing what we do in this particular the DPGA. So, once again let me repeat, we start with N, that is divided into two subpopulation N1 and N2. On N1, the GA operators will be working to find out diversification, and it is going to supply some solution to N2. The size of the N2 is going to increase with the number of iterations, and gradually the size of N1 is going to decrease and N2, the size of N2 is going to increase, and we will find that this N2 will contain all the non-dominated solution. So, we will be getting at the end a large number of non-dominated solution, and with the help of this non-dominated solution, we can draw the Pareto optimal front top solution. Now, let us see how does it work. Now, step 2, the first member or the solution of the population is assigned a positive random fitness F1. So, capital F1, the random fitness that is chosen arbitrarily at random, say might be it is 10, 20, 30 or it could be 100, 1000, something like this, and that is put into the elite set, that is N2, and that is nothing but the non-dominated set. Now, as I told that the first solution is selected at random from the initial population, and that is just put in the elite set, that is the non-dominated set, that is N2, after assigning the fitness F1. Now, let us suppose that after some time or after a few iteration, there are capital K number of solutions in the elite set E k, or k varies from small k varies from 1 to up to capital K. And let us assume that I am solving one multi objective optimization problem having capital N number of objectives, and if that is the case, then this particular E k will have a capital M number of numerical values. So, E k is nothing but the kth solution lying on the non-dominated front, and this small k varies from 1 to up to capital K, and to represent a particular non-dominated solution, that is the kth one, I am using capital M number of numerical values, because it has got capital M number of objective functions. So, this is corresponding to the first objective, corresponding to the second objective, corresponding to the mth objective, and supposing that we have got this particular the information. Now, step 3, we calculate the distance of a particular solution x from the elite set as follows. Supposing that I have got a few elite solution in the non-dominated bin. Now, I am just going to select a particular solution from the initial bin, the initial population of solution, and I am just bringing it to the non-dominated bin for the purpose of comparison. And what is the purpose of comparison? The purpose of comparison is whether I should select this particular solution for the non-dominated bin or not. Now, what we do is we try to find out the Euclidean distance between the kth solution lying on the non-dominated bin and the new solution, that is capital X, using this particular formula, that is square root of summation small m equals to 1 to capital M E m k minus f m x divided by E m k square, and using this particular expression, actually what I can do is, so I can find out what should be this particular the Euclidean distance values between a solution capital X and one elite solution. Now, this f m x is nothing but is actually the value of the objective function. Now, and E m x is nothing but its corresponding value which is there in the elite. Now, what we do is, supposing that I have got only one elite solution, so there will be only one distance values, but if I consider that we have got more than one solution in the elite set, so I will be getting more than one Euclidean distance values. Now, supposing that I have got 10 solution in the elite set or the non-dominated set, so I will be getting 10 such numerical values for this Euclidean distance. And after we have got 10 such values, what we do is we try to find out the Euclidean distance and compare those particular the numerical values. Now, we compare the numerical values of this particular dkx and we try to say for which value of this particular k I am getting the minimum of the Euclidean distance values. That means, we try to identify what is d minimum, that is the minimum of all dkx values where k varies from 1 to up to k, and we try to locate that particular value of k for which I am getting this particular the d minimum. Let me take one example. Supposing that I have got 10 such solution in the non-dominated bin 1 to up to say 10, I am just selecting a particular solution from the initial population that is brought for the purpose of comparison. we calculate Euclidean distance values. I will be getting 10 values for this particular dkx. We compare those numerical values, and supposing that out of this particular 10, say corresponding to the 6th elite solution or the non-dominated solution, I am getting the minimum dkx, that is nothing but d minimum, and k star will be equal to 6, the 6th solution. So, I think it is clear now. Now, step 4, if the solution x is found to be non-dominated with respect to the existing elite, it is accepted in the elite set and its fitness will be calculated as follows. So, this is the formula which we generally use to find out the fitness of the solution which has been selected for the non-dominated bin. So, if capital X, if it is found to be suitable for the non-dominated bin, so it will be put in the non-dominated bin and its particular fitness will be calculated using this particular the formula. So, how to select that particular, how to get this particular formula? So, this f e k star is nothing but the value of the objective function corresponding to that particular elite which gave that particular the minimum distance value, and this particular fitness is added to the d min, that is the minimum distance value, just to find out what should be the fitness for the solution x which has been selected for the non-dominated bin. Now, on the other hand, if this particular solution is not selected, let us see what happens. If the solution x is dominated by the existing elite solution, that means it is not accepted in the non-dominated set or the elite set, then how to find out or how to calculate the fitness. So, f x is nothing but the maximum between 0 comma f e k star minus d minimum. So, what we do is we try to calculate this and we compare and we find out the maximum between these two, that will be actually the fitness assigned to the capital X if it is not selected in the elite set. Now, just to summarize whatever I discussed, let me just put in this particular format. Now, I have started with a large number of population of size say capital N, say n could be 1000. The first solution you select at random from this particular population and you just put it in the non-dominated bin, that is N 2, and we assign some arbitrary fitness, say 1000 or 100 whatever may be. Now, we select the second one, we bring it for the purpose of comparison and we try to find out the Euclidean distance between the second solution and the non-dominated solution, and we try to find out by comparing its fitness value f 1 and f 2, whether it is a dominated solution or a non-dominated solution. If it is found to be non-dominated solution, so we put it in the elite set or the non-dominated set and its fitness is calculated using this particular the formula f x is f e k star plus d minimum. On the other hand, if the capital X is found to be dominated, that means that is the worst solution compared to the existing non-dominated solution. Now, in that case what we do is we do not select x for the non-dominated bin and its fitness is calculated using this particular the formula, and this process will go on and go on, and we will be getting some n 1 subpopulation solution and some other solution in the n 2, that is the non-dominated set. And as I told that this process will go on and go on through a large number of iteration. And of course, we use the operators. So, we use the operators like crossover mutation to modify the population of solution, and this completes one iteration, and this particular iteration will go on and go on, and there is a possibility the size of n1 subpopulation is going to decrease as I mentioned, and consequently the size of n2 which contains the non-dominated solution, that is going to increase. That means, if I run this particular algorithm for a large number of iteration, there is a possibility that this algorithm will become slower and slower with the number of iterations, because to store that particular n2 subpopulation, more storage space is required in the computer, and gradually. So, the latter iteration will take more CPU time compared to the previous one. So, if you run this particular algorithm for a large number of iteration, there is a possibility the algorithm will become slower and slower. This is actually one of the drawback of this particular the algorithm. Otherwise, there is a possibility that ultimately you will be getting a very good collection of n2 subpopulation, which contains all the non-dominated solution, and we can plot just to get that particular Pareto optimal front top solution. Now, I am just going to discuss. So, this particular algorithm with the help of one numerical examples. Now, let us see how does it work. Now, supposing that I have got a two objective optimization problem. The aim is to minimize the function f1, function of two variable x1 and x2, and that is nothing but x1 plus x2, and the second objective function minimize f2, the function of the same design variable x1 and x2 is nothing but 1 by x1 plus 1 by x2, and x1 x2 are lying between 1 and 10. Now, let us try to examine the nature of these two objectives. Now, the nature is such. So, this is the first is x1 plus x2, and the second objective is 1 by x1 plus 1 by x2. That means, for a particular set of value, I will be able to calculate f1 and f2. Now, if I just increase the values of this x1 and x2, there is a possibility f1 is going to increase, but at the same time f2 is going to decrease. So, what is happening is these two objectives are fighting with each other, they are conflicting. So, these are ideal problem to get the Pareto optimal front top solution. Now, let us see how to solve this type of two objective optimization problem with the help of this DPGA. Now, what we do is, lying within the range for the design variables, let me assume some numerical value for this x1 and x2. Now, x1 and x2 are lying between 1 and 10. Now, let us consider x1 equals to 4.0 and x2 equals to 5.0. Now, what we do is, we just substitute the values of x1 and x2 here, values of x1 and x2 here. So, I will be getting the numerical value for this particular f1 and f2. And as I told, the first solution is selected at random for this particular the non-dominated bin. So, what we do is, so here we select this particular solution for the non-dominated bin. So, it is going to lie in that particular EK subpopulation. So, this is nothing but the non-dominated subpopulation or the non-dominated bin. So, one is going to enter here, and we assign some fitness value arbitrarily. Let me put it is 10.00. I can also put 100 also, there is no problem, but let me put 10.00 here. So, the first solution is selected at random and that is put here in the non-dominated bin. Now, we go for the second solution. Now, once again these are all generated at random. So, I am selecting at random a particular value for x 1 that is 7.0, another value for x 2 that is 2.5, and using the same expression of the objective function I can calculate f 1 that is nothing but x 1 plus x 2. So, this is 9.5 and f 2 is nothing but 1 divided by x 1 plus 1 divided by x 2, that means your 1 divided by 7.0 plus 1 divided by 2.5, and if you calculate we will be getting 0.54. So, this is nothing but the value of the second objective. Now, if I compare, our aim is to minimize both f 1 and f 2. Now, if I compare in terms of f 1, so the elite is having 9.0, this is the elite solution now, non-dominated solution, and the second solution is having 9.5. That means, second solution is a worse solution compared to the non-dominated solution, that is 1. Now, I compare the objective function value f 2 and corresponding to the second solution it is 0.54, corresponding to the elite or the non-dominated it is 0.45. Once again second solution is a worse solution in terms of f 2. That means, solution 2 is found to be dominated or the worse compared to the non-dominated solution that is 1 in terms of both f 1 and f 2. So, this is a bad solution, this should not enter in the non-dominated bin, and that is why the second solution I did not put it here. And you see the elite set will contain only the first solution. Now, once I have not put, then how to find out the d minimum and how to find out the fitness, that I am going to discuss. To find out the d minimum, as I told, so now I will have to compare these two in terms of f 1 and f 2. That means, I will have to compare 9.0 with 9.5, 0.45 with 0.54, and I will have to find out what is that particular the Euclidean distance value. How to get it? So, I am just going to discuss that. To get that particular the Euclidean distance values, actually what we do is, so we try to find out this dkx, that is nothing but square root 9.0 minus 9.5 divided by 9.0 square, the formula I have already discussed. So, 9.0 is corresponding to actually the elite one, that is a non-dominated one, and 9.5 is corresponding to the solution capital X, the new solution, that is the second solution. Similarly, 0.45 is corresponding to the non-dominated and 0.54 the value of the second objective, this is corresponding to the second solution. So, we try to find out the Euclidean distance value, and it is coming to be equal to 0.21. Now, as I told, there is only one elite solution till now. So, there will be only one Euclidean distance value, and that is nothing but the d minimum. So, d minimum we are able to calculate, that is 0.21, and as this particular solution is not selected for the elite set, it is a dominated solution and its fitness will be calculated using that particular formula which I have already discussed, that is nothing but the maximum between 0 comma E k star, if we remember, that is nothing but the fitness corresponding to the non-dominated or the elite minus d minimum. Now, if I calculate this, so I will be getting 10 minus 0.21 is 9.79, and the maximum between 0 and 9.79 is nothing but 9.79. Now, now I can assign this particular the fitness to the second solution. That means, I will be getting so this particular 9.79 here. So, this particular fitness I will be able to calculate, and I will be able to calculate the D minimum, and as I told, this is not going to enter the non-dominated bin. Now, let me concentrate on another solution, that is the third solution, and once again this is selected at random, the values of x 1 and x 2 lying within the respective ranges, and very easily I can find out f 1 is x 1 plus x 2, f 2 is 1 by x 1 plus 1 by x 2 is 0.7, and now I will have to compare the values of corresponding to the solution 3 with that of solution 1, that is the non-dominated one, in terms of both f 1 and f 2. That means, I will have to compare this 9.0 and 7.0. Similarly, I will have to compare 0.45 and 0.7, and both are minimization. So, in terms of f 1, solution 3 is a slightly better solution compared to solution 1. That means, solution 3 is a non-dominated solution compared to solution 1 in terms of f 1, but in terms of f 2, solution 3 is a worse solution compared to the solution 1. Okay. Now, if this is the situation, so in with respect to one objective, solution 3 is a non-dominated, but with respect to another objective, solution 3 is a dominated one, that is the worse compared to solution 1. Now, in that case, we give a chance to solution 3 to be there in the non-dominated front. So, that we just want to give some chance initially, because there is a possibility through a large number of iteration this particular solution is going to improve itself, and we do not know ultimately it could be a very good solution in future. That is why we just want to give some chance to this particular solution, although it is not found to be non-dominated compared to solution 1 in terms of both the objectives. So, what we do is we give a chance because it is found to be better compared to solution 1 with respect to at least one objective, and we put it in the non-dominated bin. That means, solution 3 is put in the non-dominated bin. So, there is updating of this particular the non-dominated bin. Now, how to calculate the Euclidean distance and the fitness, that I am going to discuss. So, here as I told that we will have to compare with the elite, that is nothing but your this 9.0 corresponding to the first solution, and 7.0 is corresponding to the third solution. So, 0.45 is corresponding to the first solution value of f 2, and 0.70 is the value of f 2 corresponding to the third solution, and if you just calculate. So, I will be getting this particular dkx, and I will be getting once again only one value for the Euclidean distance. So, that is coming to be 0.60. So, this is nothing but the D minimum. So, the D minimum we can declare is nothing but equals to 0.60, and the solution 3 is found to be non-dominated with respect to at least one objective. So, we put it in the non-dominated set or the elite set, and its fitness will be the fitness of the elite plus the D minimum, that is 0.60. So, this will become 10.60. So, what we do is we put this particular your the values of the Euclidean distance and the fitness in this particular the table. Now, what we do here, I have considered only 3 solutions. Similarly, this method will go on and go on, and it will go to all the solutions, checking for all the solutions lying in the population, and gradually you can find out. So, this particular subpopulation is going to, size of this is going to increase, and the solutions which are not selected for the non-dominated bin, they will be put in another subpopulation, that is the N 1 subpopulation, which will participate in crossover. So, this is the crossover and mutation. Now, this particular process will go on and go on through a large number of iteration, and ultimately we are going to get a very good non-dominated front, that is N 2 subpopulation. And if I just plot this N 2 subpopulation at the end of a large number of iteration, there is a possibility you will be getting the Pareto optimal front top solution. So, this is the way actually using this particular method. So, we can find out the Pareto optimal front top solution, but one demerit which I have already mentioned, it is computationally expensive, and with the as the iteration proceeds, the complexity, computational complexity of this particular algorithm is going to increase. That is actually the major drawback of this particular the algorithm. Thank you.